I usually like to give these tips to you and these advices to you so that you always learn with your end in mind. You have a target to go. Okay, tak ada you belajar and you don't know how to relate eventually and tak tahu ni untuk apa, itu untuk apa. If you have your end in mind, your destination, at least, you know, a couple of companies, a couple of industries, so you can polish your fundamentals accordingly, right? So you have a target to go for, right? All right, generation and recombination. When you do device physics later on, then you'll come back to this slide. Trust me. You will look for this slide when you work. So keep these slides properly for your career. It's going to help. So I have a few cases ready for from my previous students. And I grad few years, email me asking for the slides. Because the contents are similar to what they're doing in the industry. So trust me, you're going to need this slide. It's a matter of time. Okay, right. So can you see the slides on the screen? Good. All right. Yesterday we have discussed a little bit on carrier generation, especially on absorption of light. So we have discussed on what happens to incident photons upon their incidence on a semiconductor surface. So we've learned that some portion of the light or some portion of photons will be reflected off the interface upon the incidence, and this is dictated by the difference in refractive indices between the two media, air and silicon in this case. And this also happens even when the photons are going out at the back, right? So they're going to see another interface where they're going to travel out of silicon into the air, and there'll be some interfacial reflection as well. So we call that as interfacial reflection because the reflection happens at the interface between two neighboring media, right? Interfacial reflection. And the photons or the light that's not reflected off the interface will be absorbed, and that depends on the three cases, remember? So let's recap what are the three cases that each photon will experience upon interaction with the semiconductor that we learned from the website yesterday. Can you recall case 1, case 2, case 3 before we move on? Anyone? You can unmute yourself, can write down in the chat box as well. What is the first case for the photon with regards to its energy? Its energy? On someone? Sofudin, what's the first case for the photons? Okay, Fada, EPH less than EG. Right, thank you. Case number 1, EPH less than EG. So let's elaborate a little bit on this case number 1. So will there be any excitation of the valence electrons into the conduction band for this case? No, there's no excitation. Good, because the energy possessed by the photons is not enough to excite the valence band electrons across the band gap. So that's why you're comparing the photon energy EPH with the band gap, right? So for this particular case, if you're talking about crystalline silicon, then we're talking about overcoming 1.12 electron volt. If you're talking about cadmium telluride, you're talking about overcoming 1.4, 1.5 electron volt. If you're talking about perovskite, you're talking about overcoming 1.6, perhaps 1.7, depending on the band gap, because some semiconductors, the band gaps can be tuned. You can actually change the band gap to some extent. So there's band gap tunability properties of certain semiconductors. But if you talk about crystalline silicon, it's fixed, 1.12, right? Right, so there's no optical excitation, and the valence band electrons will remain in the valence band, and there is no light absorption. Okay, so let's talk about case number 2. What about case number 2? Tadi Farah dah bagi case number 1. Okay, bala case number 2, EPH equals to EG. Right, energy possessed by the incoming photon, by the incident photons, is equal to the band gap. So in this case, do we have any light absorption? Yes. So since we have light absorption, do we have excitation of valence band electrons from the VB to CB? Yes, right? So the excitation of valence band electrons from VB to CB follows the light absorption, okay? When you have the light absorption, then energy too, you have to conserve, then it turns into the excitation, right? So how about case number 3? EPH more than EG, very good. EPH more than EG. So in this case, do we have any light absorption? Yes, all right. We have light absorption because the fuel is more than enough to travel, right? So the energy is more than enough to overcome the band gap, 1.12 for crystalline silicon. Then what happens to this particular case when the electrons are excited further up into the CB? What happens next? That differentiate this step. Thermalization, very good. Thermalization of electrons back to the band edge. All right, CBH, conduction band edge. Good. So clear. So kalau if there's any question on the 3 scenarios of photon upon incidence on any semiconductor surface, these are the 3. EPH less than EG, EPH equals to EG, EPH more than EG, right? And there'll be some portions of the photons or some portions of the light that will be transmitted at the back of a semiconductor. Okay, so among the 3 cases we discussed, so which case falls into this category? Case mana yang exhibits or has this photons transmitted? Third case, which scenario presents photons that are not absorbed? Remember, whatever that's not reflected goes into silicon, and some will be absorbed, some will not be absorbed. So which one are not absorbed? Case mana yang tak ada absorption tadi out of the 3 that we discussed? Yes, transmission, but first case, right? Good for that. First case, yang mana photon with energy less than EG, case number 1, So because the energy is not enough, so the photon will just pass through the silicon or whatever semiconductor lah, sama aja, konsep dah sama aja. I'm going to talk about silicon, but it applies across other semiconductor materials as well. So when the EPH is less than EG, the semiconductor material will appear to be transparent to the photons. Macam walaupun you are holding an opaque silicon, I don't have my silicon now. Katalah ni, this is my phone. Just imagine this is my silicon wafer. It's opaque. You cannot see through, right? So it's opaque. But to the photons, with energy EPH less than EG, this semiconductor material will appear as transparent to the photons. Tak transparent kepada kita lah, but transparent to the photons because of the energy possessed is less than the band gap energy. So that means if you have photons, if you're talking about crystalline silicon, then the photons must have energy of less than 1.12. So let's say if your incoming photons, for example, the energy is 0.9 electron volts. So what happens to this photon? Will it be absorbed or will it be transmitted if it interacts with crystalline silicon? 0.9 transmitted, right? Because it falls under this category. Okay, dia akan transmitted kat belakang. So if you talk about nanti you're going to learn a lot more with Dr. Marzani on solar spectrum when you talk about solar cell. Solar spectrum, let me just give you a brief. We have been, looking at the sun every day, right? Except when you cannot see the sun when it rains too heavily. Our sun has a spectrum. Just an intro for this. So our sun has UV component okay, below 400 nanometer, and it has a visible component 400 to about 780 or 800 close to, and here is near infrared, and going forward is infrared. So you can then relate. So you have been, I think you have been learning in your first year and second year how to convert wavelength into photon energy, right? You know already how to convert, isn't it? If I tell you the photon wavelength is 800 nanometer, for example, then you already know how to convert to photon energy, isn't it? Done? Have you learned this? Pakai simple equation kan? Tak lupa. I think you learn somewhere, isn't it? In previous course, kau tak belajar lagi? How do you convert photon energy to wavelength? How do you then convert wavelength to... you learned but forgot. So how do you convert wavelength to photon energy? How do you convert photon energy? So EV lah, EV, whatever EV to wavelength, whatever wavelength to EV. Calculator ada online. You can look at the equation and use calculator to convert. So when I'm saying that a photon has a specific wavelength, so it has a specific energy as well. Okay, so you can then convert, say 800, so it corresponds to say 1.6, 1.7 perhaps, and then you can relate to this, and then you can relate to this. Okay, if you want to work in semiconductor, solar industry in particular, and this is the thing, okay, because it's all about light absorption, photon carrier generation. You're going to learn it from. Okay, if you want to work in solar cell industry in Malaysia, this is the thing. Okay, so you have to be able to relate to whatever spectrum that you have, and what is the wavelength, the energy, and then what is coming on the silicon or whatever. Yeah, thanks, Fada. Right? E equal to hc over lambda, Planck constant times speed of light over wavelength, and the wavelength is this wavelength. Okay, and the E there is the energy, is the photon energy in the electron volt. Okay, then you can then convert back and forth from lambda to EV, okay, or EV to lambda accordingly. Yeah, just rearrange the equation, simple. Yeah, okay. So next, when you have light absorption, when you narrow down into this, okay, still on absorption of light, different semiconductors have different capabilities of absorbing light, and that is determined by the parameter called absorption coefficient, or alpha. Right, the higher the alpha, the better the light absorption capability by that particular semiconductor. Okay. The lower the alpha, or the poorer the light absorption capability by the semiconductor. Right, alpha determines how far into a material of a particular wavelength can penetrate before it is absorbed. How far it penetrates into a depth. So what does it mean? Maksudnya, if your alpha is very high, most of the photons will be absorbed close to the surface already. Maknanya masuk dia absorb terus, because the alpha is already high. On the other hand, if your alpha is low, you need more depth. Maknanya dia kena masuk dalam. You have to have a lot of volume lah. You have to have a lot of thickness, high thickness, in order to make sure your photons are completely absorbed. Okay. Yes, ataupun you need to have a high optical path length. Optical path length tu maknanya distance traveled by the photons before they get absorbed. Okay, maknanya kalau high alpha, masuk ke surface je dah absorb, completely absorbed, because the material is very efficient at absorbing light. On the other hand, if alpha is low, you need quite a depth of material, quite a thickness of material, in order to ensure a complete absorption of the photons, right? So low alpha light is poorly absorbed. Okay, poorly absorbed. And if the material is thin enough, it will appear transparent to that wavelength. So that means, just like what I explained, kalau alpha is very low, the material has a very poor light absorption capability. So that means you need relatively thick material in order to ensure light absorption. So kalau you compare dua different material, alpha high, alpha low. Alpha high, my right hand, alpha high, alpha low. Then you have the same photons incident on material alpha high, alpha low. So this alpha high only need a fraction of thickness in order to ensure complete light absorption, complete photon absorption. On the other hand, alpha low material needs a very thick thickness. Katalah yang alpha high perlu banyak ni je, just to show some relative thickness, and alpha low needs this much in order to absorb the very same set of photons incident. Okay, maksudnya when you translate this into industry, you need more material. You need to spend on more material to be able to ensure similar light absorption between this and this. On the other hand, for this industry, you only need this much of material, hence the cost to be able to ensure the same light absorption capability, right? We're going to learn it on the next page. Don't worry yet. So alpha depends on material and also the wavelength. Alpha, one more thing, is also dependent on whether it is the semiconductor is direct or indirect bandgap. Which one do you think, based on our previous knowledge, which one do you think left is indirect, right is direct? Indirect, direct. Between indirect and direct, which one do you think has higher alpha? Based on the previous knowledge. Indirect or direct? Mana yang lagi senang absorb the light? Which one is more efficient at absorbing the light? Okay, Bala say indirect. Bala say indirect. Any more answers? Any different answers? Alisa, what do you think? Alisa? Sofiuddin, Fathul, Najiha. Just write down your answer. It's right. Let's discuss. Yang mana yang you rasa more efficient at absorbing the light? Indirect or direct bandgap? Based on what we learned before. Based on the structure of your apa ni? Conduction band dengan band apa ni? Valence band. Any other answers? So we have two indirect. Patient, what do you think? Which one is more efficient? Yang mana yang lagi senang? Which one is easier for the valence band electrons? Patient think it's direct. Okay. Any other answers? Others? So yang mana lagi senang? Yang mana lagi efficient? What I mean by that is, which one is easier to have optical transition from the max of your VB to the min of your VB, min of your CB, sorry, max of your VB to the min of your CB. Yang mana lagi senang?
Doctor, you mean smaller alpha, is it?
I mean higher alpha. Which one has higher alpha? Higher alpha is more efficient at light absorption.
Oh, that means direct.
Okay, Bara said direct. Okay, Fatul said direct. Okay, so the answer is direct bandgap. Sebab apa? Sebab direct bandgap. Fatul, recombination process is much more efficient, direct bandgap. Yes, that is recombination, which is essentially the opposite of absorption ataupun generation. Okay, so remember yesterday we discussed for you to have an optical transition in let me pronounce this correctly, in direct bandgap, bukan indirect indirect bandgap lah. Indirect bandgap semiconductor, you only have to have, bukan you lah, valence band electrons need to have a vertical transition and that's it, right? On the other hand, in indirect bandgap, you need to have a vertical transition plus the phonon component on the horizontal axis. You can ada dua step lah. For example, if you want to travel to from Seberang Jaya to USM, it's just through the first bridge and then turun dekat bridge over the island dah sampai kat Minden. On the other hand, for the left case, you're traveling from Seberang Jaya, then you want to go to Georgetown ataupun Tanjung Tokong ke, Gurney, perhaps you have to go to the right. So it's a lot harder for you to arrive, isn't it? It's a lot longer for you. Yeah, the vector is longer. So that means the direct band gap usually has a higher alpha and a lot easier to absorb. Okay. Semiconductor materials have a sharp edge in the absorption coefficient since light, which has energy below the band gap, doesn't have sufficient energy. So this is essentially EPH less than EG. Okay, yang energy tak cukup lah. So then the light is not absorbed and transmitted at the back, just like we discussed on the previous page. So let's see here. The absorption coefficient alpha in, hold on, let me turn on. Absorption coefficient alpha in a variety of semiconductor materials at 300 Kelvin as a function of vacuum light as below, right? So this is the alpha against wavelength. So let's have a look. Crystalline silicon is an indirect band gap, therefore a poor light absorber. Okay, indirect band gap, poor light absorber, and low absorption coefficient. So that means crystalline silicon needs a very high thickness in order to completely absorb the light. So if you talk about the application for solar cell, then you're talking about absorbing solar spectrum from the sun. Even though you can use a monochromatic light like LED white light or something, you can use as well. But if you're talking about the sun, then you have UV, visible, and IR component. So to be able to absorb UV, visible, IR, crystalline silicon needs a relatively thickness. Okay, so let's compare. Where is crystalline silicon in this case? So let's see. Silicon here is a crystalline silicon. The red here is crystalline silicon. Okay, tapi dia tulis kat tu silicon je lah. You can get this from PV Education website as well. So let's have a look. So at 600, so typically our solar spectrum peak around 600 nanometer. So this is where you want to harvest the most. So that's why when you do the comparison of the alpha, try to compare first at 600 nanometer. So that is crystalline silicon. So that's about what, 2, 3, perhaps early 10 to the 3, low 10 to the 3, right? Low 10 to the 3 cm minus 1. So let's compare with gallium arsenide, right? Crystalline silicon being indirect band gap and gallium arsenide is direct band gap, blue. So if you compare with gallium arsenide, so that's like high 10 to the 4. High 10 to the 4. So one order of magnitude of difference between crystalline silicon and gallium arsenide. So that means in order for gallium arsenide to completely absorb the light from the sun, in this case, for this particular example, you need only about 2 micron of gallium arsenide. 2 micron of gallium arsenide with this absorption coefficient, you only need about 2 micron or so of gallium arsenide in order to completely absorb the light from the sun. On the other hand, what do you think is the thickness required for crystalline silicon? You need about 200 micron. And that is still not enough, actually. You need to have some optical strategies in the crystalline silicon, even at 200 micron. So you need 200 micron in comparison in order to completely absorb completely. So that's like 2 orders of magnitude in thickness that you have to spend on your material in industry in order to completely absorb the very same spectrum of light. Okay, so that is the impact of alpha. Okay, and this goes back to the direct band gap or indirect band gap concept, right? So maksudnya the physics is direct band gap, indirect band gap leads to alpha, leads to light absorbing capability, but the industry aspect is the economics of it, right? You want to absorb the light so that you produce enough current in the solar panels on the roof, and on the other hand, you have to spend much more money on 200 micron of silicon compared to 2 micron of some other direct band gap materials. So that's the economics. So maksudnya what we learn in physics, you can stretch that to industry and economics and stuff. But it boils down to physics. Okay. Right. So absorption depth is another thing, which is the inverse of alpha. Absorption depth is essentially 1 over alpha. So let's go through for another perhaps 10 minutes. Absorption depth is given by the inverse of absorption coefficient, or 1 over alpha. Ataupun alpha -1 lah, inverse -1. Absorption depth means distance into the material at which the light drops to 36% of its original intensity, or alternately has dropped by a factor of 1 over E. Okay, so that means when you have a crystalline silicon or gallium arsenide, cadmium telluride, gallium nitride, indium phosphide, perovskite, organic material, whatever. So absorption depth is defined as you have your photon intensity hitting 100% on the surface. So the moment your photons are penetrating into the material and the intensity drops to 36% of its original intensity, so the point or the depth at which the intensity is dropped to 36% is called absorption depth. Okay, maknanya as it goes into the material, photons will be absorbed, so that you're going to lose your intensity, right? Because the photons is absorbed. So sampai mana dia travel until the original intensity is only left with 36% if you compare to 100% on the surface. So that is absorption depth. Okay, so you can try to press your calculator now. If you try to press 1 over exponential to the power of 1, what do you get? Cuba tekan calculator. One over exponential to the power of 1, or 1 over E lah. 1 over E. What do you get? Anyone? You can share in the chat box. Anyone got anything? 1 over E, 1 over E, yes. E to the power of 1, to the power of 1. Anyone? Right, so 0.367, Sophie, right? Good. So that's this 36%. Sama, huh? So it's dropping by that amount, to that amount, right? So high energy short wavelength, high energy short wavelength light such as blue light has a large absorption alpha, absorbed in a short distance on the surface, while red light, lower energy, longer wavelength is absorbed less strongly. Okay, so that means that's why I discussed about the photon energy to wavelength conversion, as what Fada mentioned now in the chat box. You need to use this equation, and you will see that when you have high energy photon, you have low wavelength because they are inverse to each other, or they are reciprocal. On the other hand, when we talk about low energy photons, you are talking about high wavelength. And for light absorption, the photon with high energy will be absorbed at the surface. High energy means low wavelength. Okay, maksudnya if you're talking about solar spectrum, for example, the UV portion will be absorbed at the surface. The visible portion will be absorbed slightly into the volume of the material, and the IR portion will be absorbed at the back or close to the back, depending on the thickness and alpha, of course. So maksudnya kalau you have say 100 micron of this material, so most of the UV light will be absorbed in the first hundreds of nanometers. Gone. UV is already absorbed. Bila you go beyond that, the visible will be absorbed. If you're approaching the back, IR will be absorbed. Maksudnya, the order of light absorption will be in that order. So it's not like you have the material will absorb all the photons at the same time. No. Maknanya dia ikut volume. So that's why bila you design the volume of your material in industry later on, if you design it too thin, then only UV portion will be absorbed. Your visible IR akan keluar kat belakang sebab volume is not there to absorb. Right? By the time visible sampai kat belakang, it's already meeting the air interface. Gone. Dia akan keluar kat belakang, transmitted. So you have to design the material thick enough to be able to absorb most ataupun all, ideally. So let's go to this website and see what do we actually get from this. Let me share again the website yesterday. Share content. Oh, sorry. Share. Then. Okay, can you see the website on the screen? Just to confirm.
Yes, doctor.
All right, good. So this is where we discussed yesterday, the 3 cases, remember? So let's have a look at the next page, coefficient. So this is the very same graph I presented is now on the slides. You can see the comparison and you can read the explanation on the alpha, low, alpha, high, all those stuff. So all are here already. Let me just go to the next page, absorption depth. Okay, so absorption depth, as I said, is the inverse of alpha. You can just take the alpha on the previous page, inverse the alpha, and you're going to come to this y-axis absorption depth. So remember alpha is 1 over cm or cm minus 1. So then the inverse of the alpha or the depth will be cm. Otherwise you can change that to nanometer or microns, but then the value on the y-axis will change accordingly, right? But this one is cm. So you can still change this to nanometer or micron accordingly from the current unit. Okay, so that's what it is. So I would like to show you this animation with regards to light absorption at the surface, in the volume, and at the back. So remember, high energy photons, UV, low wavelength will be absorbed at the surface. So now you have a look at the blue photons. So blue photons are the high energy photons. Blue here is to denote the UV region, ataupun short wavelength lah. So you can see that the blue photons are absorbed at the surface. Sampai surface they are all gone. They are all absorbed already. On the other hand, if you compare to the red, you can say that these red photons are near infrared, perhaps. You can see that they are absorbed at the back, isn't it? So kalau you include another one like a green or yellow, then where do you expect to get absorption? By the order of the wavelength. Can you see this animation? Nampak kan? Right? Okay, balance it middle. Okay, you can see. So the blue is about, say, 400 nanometer if you're talking about just starting point of the visible. At the point, if you talk about UV photon, then you're talking about below 500 nanometer. So those will be blue photons, absorbed right at the surface. Okay. On the other hand, red is absorbed at the back. So if you're saying a red is like 800 nanometer, for example, or perhaps more than that, then they will only be absorbed at the back. So just imagine this Y, this whole thing is your thickness, right? So kalau you punya thickness ni tak cukup, just imagine if you halve this thickness, area sama, thickness you halve, so that means your volume is reduced quite significantly. So that means there'll probably be transmission of red photons at the back. Sebab photon baru saja sampai dekat halfway or so, but then the volume is already finished. Bila sampai dekat hujung crystalline silicon dah tak ada. It's no longer present. It's already silicon to air interface. So that means the red photon will be absorbed at the back, will be transmitted at the back. Okay, so that means you need to supply enough volume, enough thickness, assuming the same area, because volume is area times thickness. You need to supply this sufficient thickness in order to ensure blue are absorbed, yellow, green are absorbed, and red are absorbed as well. Okay, and the greens and the yellows will be absorbed in the middle, correct? Because they are visible, right? So the question here, does that mean if we really use thin thickness for solar window purpose, for example, 100 of the thickness, the light absorbed is mostly UV photon? You can say that literally, but that does not necessarily mean so, because it depends on the absorption coefficient of the material. So if you're talking about a perovskite, for example, which has a very high alpha value, so you can already absorb most of the light or most of the photon with a very thin thickness. But if you're talking about 100 nanometer, then you can absorb a lot but not complete. Okay, and that's why the optical strategies comes in the design of solar cell. Okay, my PhD last time was in light trapping schemes of photons in solar cells. So that means that I only need to use somewhere around 10 micron of crystalline silicon instead of 200 micron. But at the same time, I need to ensure that most of the photons are absorbed. So that means you need to stretch the capability of the crystalline silicon. So that means you need to incorporate more optical strategies in order to trap the light, trap the photons. Maksudnya volume yang you ada just banyak ni ya. So in principle you can only absorb this much. But how do you then absorb most with only this much of thickness of crystalline silicon? And that's involving optical strategies like reflectors, textures. So those all in all is called light trapping. Okay, how do you trap photons? So that was my PhD. Okay, so do you understand now the concept of this blue photon, red photon absorption against the depth? Okay, is it understood? Yeah, good. You can always come back to this animation, yeah? So it's very clear already, right? Tak paham nanti you just come to this and read the explanation. So essentially you need to have enough volume of material in order to ensure complete light absorption. So this is what's happening in the industry before I finish. So industry, let me just give you some perspective if you're interested to work in solar industry. If you now crystalline silicon represent 90% of the whole PV panels manufactured in the world because of a couple factors. Mainly because it's a mature technology. We have extended knowledge from IC fabrication. We have textbook, we have a lot of references, we have expertise. Industry is already familiar with silicon in comparison to some other semiconductor materials. And silicon has a relatively good light absorption, even though if you compare to the direct backend semiconductors, it is a lot poorer. But you need to ensure for manufacturing of silicon, crystalline silicon, the thickness has to be very thick. When the thickness has to be very thick, that means you need to spend a lot on the material, spend a lot of money on the materials, right? Kalau tidak, your visible and your IR will not be absorbed. So that increases the operation cost, right? So, and if you increase the operation cost, the technology cost of solar, which uses a dollar per watt, USD per watt as the technology cost benchmark, will be very high. So if that's very high, it cannot compete with fossil fuels, and the technology will not be adopted by the people, by the society. On the other hand, if you want to make the technology cost cheaper, one option is to go for thinner crystalline silicon. But if you go for thinner crystalline silicon, the crystalline silicon will be suffering from poor absorption because thickness tak cukup lah. Thickness tak cukup to be able to absorb the solar spectrum completely. So these are the things that you need to understand and you need to comprehend when it comes to the manufacturing. Okay, maksudnya whatever that you learn in physics may not be the ideal case in the industry. So in physics, you want to provide as thick as possible in order to absorb everything. But when it comes to the industry, it's too high cost. Tak boleh, terlalu mahal, too thick. You need to reduce the thickness. But when you reduce the thickness, you are losing the photons, right? Because some will not be absorbed. So how do you then engineer the solar cell, the technology, to still ensure the photons are absorbed despite operating at low thickness? That's the knowledge of physics that you have to use. So maksudnya physics that we learn here is only the fundamentals for you to steer around when it comes to the technology development. Pergi sini, then you have this limitation. Pergi sini, then you have another limitation. So the limitations are all physics. Okay. But when it comes to industry, there are things that you cannot realize because of the operation limitation, cost limitation, engineering limitation, and some other limitations. So that's why it's very important to understand the physics. Bila you paham physics, then you tahu you have this limitation going to the left or to the right. Kalau you tak belajar the physics, then you can just, okay, let's just reduce the thickness and see what happens. See what happens to is the physics. See what happens to is the understanding that we are learning now. That's a device physicist in your job. If you're working in R&D for solar industry, this is the thing. Kalau your top management wants to reduce the thickness and ask you to evaluate the impact of the thickness reduction to the efficiency of the cell. So these are the physics. Okay, so that's why learning physics is crucial for you to before you can apply. Right. So is there any question from this class? Is there anything that you don't understand? We'll continue with the rest tomorrow. And then remember the weekend class, 2 hours. We're going to have on Saturday 10 to 12. We're going to cover the lost classes before, right? No question for now. Okay, can you follow? Now do you understand the alpha? Absorption depth, 1 over alpha. Photons absorption, blue, visible, IR, thickness required, comparison between alpha of different semiconductor materials. All good? Right. If there's no question, then I'll see you tomorrow. Bye-bye. Take care. Assalamualaikum.